Hello, welcome back as we continue to explore the respiratory system. This is part 2 of 3. I am Professor Young, and we are making our way to the finish line as we are midway through the respiratory system, heading into the urinary system, and then eventually working our way through the digestive system. No pun intended in that. And so hopefully we are doing well. The last WIMBA session that we were together for, we explored exactly how the respiratory system is able to move air in and out. Structures were gone over in lab and things like that, and so we didn't spend really too much time with that. I'm going to assume that you have looked over that and reviewed that, and that you are familiar with all of that information concerning that. And so what we need to now continue to look at here is really what is happening beyond the lungs, what is happening in combination with the circulatory system. We know that the respiratory system and the circulatory system are so closely intertwined with one another. And so the question becomes, how exactly are these two systems that do very different things but yet share some of the common physiological features, how exactly do they coexist? A couple of things that I want you to keep in mind. We know that gas is going to diffuse down a concentration gradient. So in other words, if we have more gas over on side A and less gas on side B, that those gas molecules are going to move from A to B. We also know that in part, if you would, these concentration gradients are going to be dictated or controlled by partial pressure of the gases. Again, partial pressure simply refers to the fact that we are going to look at not the whole gas, but one specific element of that gas. So the atmosphere we know is made up of nitrogen and oxygen and carbon dioxide. We know that there is methane gas and that there is water vapor and there's ozone. And there's all these other little types of chemicals that make up our atmosphere. While the atmosphere is the total gas pressure, if you would, or atmospheric pressure, partial pressure for us is what's the pressure being exerted by oxygen? What's the pressure being exerted by carbon dioxide? And so it's partial pressure in that sense. And the other thing that we need to keep in mind here is that we are not diffusing gases from air to air. The respiratory and cardiovascular junction, if you would, presents that specific challenge of now we're diffusing a gas from air into fluid. And that means that when we talk about concentrations being equal, it gets thrown out the window. We have to focus on pressure being equal because gases are not going to occupy the same concentration in both air as they do in liquid. And so the goal here is to equalize the pressures between the air and the liquid. In this case, equalize the pressure between the alveolar sacs and the cardiovascular system. Solubility is simply referring to how easy a gas is going to dissolve into a solution. And as I just got done mentioning, these solubilities, if you would, are based on gas pressures. And so under low pressure, we are going to have a high solubility of a gas. And under high pressure, we will have a low solubility of that gas. Don't dwell on that part of it too much, but that's just one of the things that you need to keep in mind. And at the same time, we want you to remember that this whole process of gas, oxygen, and or carbon dioxide, respectively, meets this challenge of having to diffuse across medium, in this case, water. And that we refer to that as the alveolar gas exchange. Remember, each of the little alveoli are surrounded by that little bubble or pocket of water. And so that equals a specific challenge for us that we must meet. And we meet that by pressure gradients, and we consider those pressure gradients that apply to oxygen and carbon dioxide across this watery membrane as the alveolar gas exchange. So, as we look through this, I want us to kind of picture, if we would, that we have air within a container that has a partial pressure of 100 millimeters of mercury. And we're just saying that's what the partial pressure is. And that's pretty close to what it is within our alveolar spaces. It's actually about 104. But 100 is a nice round number. Water initially has a partial pressure of 0. When the two touch, we would expect that the oxygen would move from the air into the water. But again, here's that key moment for us. It's not going to be equal concentrations. It is going to be equal pressure. And so if we wanted to see that in picture form, here on this side, we can see that we have our oxygen within the air, and then on this side, we have no, hold on one second, that was ugly. We have no oxygen within the fluid. As those molecules of oxygen begin to move, they collide into one another, and in this end result, down over here, what we see occurring is concentration being equal. I'm sorry, pressures being equal. We have 100 millimeters of mercury over here, and we also have 100 millimeters of mercury up here. You can look at this and you can say concentration is definitely not equal. There's a lot more air molecules, oxygen molecules, within the air than what there is within that water. So yes, we understand concentrations are not equal, but the pressure will be equal. By now, hopefully you are saying, yes, all right, this is making sense. Concentration will never be equal. Pressure will always be equal. And that is what's going to move carbon dioxide and oxygen across that watery membrane separating alveolar space from circulatory system. That pressure is what's going to allow oxygen to diffuse out of the cardiovascular system into the tissue wherever it is throughout the body, and vice versa for carbon dioxide. If you have that, if you're grasping that, then you are well on your way, and this here shouldn't throw you off too much. Carbon dioxide is approximated to be about 20 times more soluble than oxygen within water. In other words, water is more likely to hold on to and retain carbon dioxide than what it is to allow water to go through. And so you need to kind of keep that in mind. Excuse me, sorry about that. As we go through and we begin to look at the partial pressures involved with loading and unloading oxygen and carbon dioxide. And they are terms that we will tackle, I think, in the next WIMBA session. No, we won't. We'll tackle it way before then. Yep, like now. Henry's law is a law that, for us, simply states that the solubility of gas is going to be based on pressure of the surrounding air for that water given a certain temperature. So the temperature doesn't change, or at temperature A, the amount of gas that will dissolve into water is based on the partial pressure within the air. And so that is what's going to, for us, dictate this concept of loading and unloading. The act of moving oxygen and carbon dioxide is called CO2 unloading, or O2 loading, or O2 unloading and CO2 loading, depending on what it is. This is always done from the perspective of the blood. And so if we have, if we are within the lungs, we know that oxygen is going to move from the alveolar space into the capillaries. That is oxygen loading, because you are loading the cardiovascular system. You're loading those blood vessels. Now, if you follow that blood vessel down and through the body until it reaches the tissue portion where the capillaries are going to be, and that oxygen will then unload as that oxygen leaves the cardiovascular system and goes into the tissue. In the same respect, that same tissue capillary junction there, carbon dioxide will be loaded into the cardiovascular system. So it's going to leave the tissue and go into the cardiovascular system and make its way up and around to the lungs, where that carbon dioxide will be unloaded. The other thing to keep in mind is that the greater the partial pressure is, the more of that gas that is going to be moved, or the greater difference between the partial pressures, the more of that gas that is going to move. So if you have a much higher partial pressure within the alveolar space than what you do within the capillaries for respect to oxygen, you are going to load a lot more oxygen into the capillaries. And we'll talk a little bit more about that here in a few seconds. Before we do that, though, we need to look at some other factors that are going to affect how exactly these gases are loading and unloading. So in other words, the amount of time that the blood, or the red blood cell specifically, is going to be within that alveolar capillary, the capillary that is surrounding the alveoli. The longer that red blood cell is there, the more oxygen is going to be allowed to be loaded onto it. Typically speaking, it takes about a quarter of a second to load and unload within the alveolar spaces. The average time that the red blood cell spends within the alveoli is about 3/4 of a second, about 0.3 of a second if we're dealing with exercise. A quarter of a second would be equivalent to, in case you are math challenged, 0.25 seconds. And so that red blood cell has plenty of time at rest even, during exercise even, for it to load and unload a sufficient amount of oxygen and carbon dioxide. 0.25 seconds is the average load time. Typically at rest, your red blood cells are hanging out for about 3/4 of a second. If you're exercising, kick it down to about 0.3. Either way, they're still there long enough to efficiently load and unload oxygen and carbon dioxide throughout the system. Here's a question for you to answer. I'm going to give you a few seconds to maybe about a minute or so to think about that and see if you can defend your answer. I would suggest grabbing someone around you and saying, hey, read that question and let me answer it to you. See if it makes sense. So at any rate, I will give you a couple minutes and I'll be back with you. All right, so that should give you enough time to think about the answer to this. True or false? Plasma with a partial pressure of oxygen of 40 millimeters of mercury and a partial pressure of carbon dioxide of 40 millimeters of mercury has the same concentration of oxygen and carbon dioxide. True or false? You should have answered and or are screaming at your computer screen right now. You should have answered false. They do not have the same concentrations of oxygen and carbon dioxide. One gas is not necessarily going to be equal to the other gas. They have different molecular weights. We know the solubility of carbon dioxide is much higher and much greater than that of oxygen. And so it's going to be, it's basically going to be able to take in more carbon dioxide to equal that same amount of pressure than what it would for the oxygen. And so no, false. They would not have the same concentrations of oxygen and carbon dioxide. So, gas exchange in the lungs and the tissues. Let's think about this. And this is where we're going to start putting to test our understanding of pressure gradients. So the normal alveolar partial pressure of oxygen within the alveoli, of course, is 104 millimeters of mercury. Within the blood that is surrounding that alveolar sac, and this is, of course, would be the venous return, the partial pressure of oxygen is 40 millimeters of mercury. And so which way would the oxygen move down the concentrations? Actually, I should change that. Concentration is really not the best word for this because we're not really dealing with concentrations at this point in time. Instead, a better word I would suggest would be down the pressure gradient. And so you should answer that the oxygen is going to move from the alveolar down into the blood. So it's going to move down that pressure gradient. You have higher pressure within the alveolar space, lower pressure within the return blood. And so that definitely is going to move the oxygen from the alveoli into the capillaries associated with the venous return. What is the partial pressure of oxygen leaving the lungs? That partial pressure is going to be, depending on how you read that question, as it exits the lung, it's going to be somewhere right around 95 or so millimeters of mercury. And that you might not know right off the top of your head, but that's what it's going to be. And if we look at the reverse of this, the arterial blood reaches the capillaries, it's going to have an intracellular partial pressure of oxygen of about 40 millimeters of mercury. So that's the tissue pressure. The arterial blood is going to have a partial pressure of about 95 millimeters of mercury. And so which way is oxygen going to move down this pressure gradient? If you said up in this case, you are correct. It's going to move from the arterial blood up into the intracellular tissue space. Again, 95 millimeters of mercury versus 40. 95 is going to be higher than the 40, so that oxygen is going to diffuse across out of the blood, the arterial capillaries, and enter into the tissue. The reason why we say it's approximately 40 is because it depends on the metabolism and how much oxygen is actually being used up. So that's the deal with that. This here is a key diagram. I would suggest you printing it out and gluing it into the inside of your notebook so that you can study it every single time that you look at it. What this is showing us is exactly how the pressure changes for oxygen loading and unloading, and carbon dioxide loading and unloading, and how the pressure gradients change as we go through the system. And so if we start up at the top, you will notice with the inspiration, in other words, when you are breathing in, that the oxygen partial pressure is approximately 160 millimeters of mercury. That's the pressure within the atmospheric gas as you are breathing it in through your nose. By the time that reaches the lungs, partial pressure of oxygen has dropped, and it's down to about 104 millimeters of mercury. A lot of that has to do with volume. We know that volume and pressure are linked. And so the greater the volume, the lower the pressure, and that's what we're seeing here. That was one of the things that accounts for that drop in pressure. Vice versa, within the alveolar sacs, we know that now this is alveolar, but we know that we would expect to have a lower carbon dioxide concentration, so that's set at around 40 millimeters of mercury for the pressure of carbon dioxide. And as we continue to journey down into the heart, we know that newly oxygenated blood is going to return back into the heart, so that can be distributed systemically. You can see the pressures there. Again, we're down to about 95 millimeters of mercury for oxygen. Carbon dioxide is down to about 40 millimeters of mercury for, again, carbon dioxide. And we have that systemic circulation once it leaves the heart. This is where you want to really focus in at, because this is one of those areas of, as you can see, loading and unloading of oxygen. And so the partial pressure of the tissue is about 40 millimeters of mercury for the oxygen. We know, if you're reading the slide, we know that the partial pressure of oxygen is going to be equal to approximately 95 millimeters of mercury. And so we're dealing with a partial pressure of tissue fluid that's at 40 millimeters of mercury. The partial pressure of the oxygen being delivered through the cardiovascular system is 95 millimeters of mercury, and so that is going to move from within the capillaries out, and that's the oxygen. On the other hand, the pressure of carbon dioxide within the tissues, and again, this is within the tissue, is, just in case you can't read that, is approximately 46 millimeters of mercury. That is, again, within the tissues. And coming in, if you would, coming in from the cardiovascular system, the partial pressure of carbon dioxide is approximately 40 millimeters of mercury, and so that's going to force, without any question, that's going to force carbon dioxide to basically come into the capillary bed, at which point in time we begin the return trek back, and so we come back to the heart, at which point in time you can read the partial pressures. This is where we're more concerned at, right in here, though, right there, because here we will have another area of, once again, loading and unloading. And so because the partial pressure of the deoxygenated blood is about 46 millimeters of mercury for carbon dioxide, we know that within the alveolar space, the partial pressure of carbon dioxide is about 40 millimeters of mercury. And so just to kind of stress that, carbon dioxide coming in, the partial pressure of CO2 is, once again, about 46 millimeters of mercury. And on the other side of the coin, we have the partial pressure of CO2, which is going to be equal to about 40 millimeters of mercury, and that is within the alveolar space. And so that carbon dioxide is going to diffuse from the cardiovascular system, from the venous supply of blood, back into the lungs, and then be expelled outward. And so that's the flow that we're taking. I would know this diagram inside and out. Make sure you can explain the relationships. Make sure you know what's happening with the various pressures. Carbon dioxide, this is something that we just kind of went through. We know that the intracellular resting partial pressure of carbon dioxide is approximately 46. Arterial is 40. That is going to lend itself to carbon dioxide basically loading at that point in time. This is down in the tissues. And so we're dealing with CO2 loading. We're dealing with CO2 loading. Loading because it's going into the arterial system. On the other end of that spectrum, the venous blood is about 46 millimeters of mercury. We can see that the alveolar space is about 40 millimeters of mercury. And so again, we're going to go from the venous blood into the alveolar sac, and that is going to leave us with what we call CO2 unloading right there. This is what it kind of looks like all put together. Again, if we divide this up between the center here, and we look at it, this side over here is the oxygen, and this side over here naturally would then be representing carbon dioxide. And so you can kind of see how things are going to be moving in. On the respects of loading and unloading, on the oxygen side, of course, we're going to be loading coming in from the alveoli into the circulatory system, and that pressure is going to be about 104. Once it reaches the tissues down below, once we reach down below into this area, that partial pressure of oxygen is down to about 95, and but it's still greater than the tissues that it's at, which is at around 40 millimeters of mercury, and so it will, down in this region, experience unloading. So that oxygen will unload and go into the tissues. Likewise, the opposite can be said for carbon dioxide. The partial pressure of carbon dioxide as it approaches the tissues is about 40 millimeters of mercury. The partial pressure within the tissues of carbon dioxide is 46. 46 is greater than 40, and so we are going to be experiencing loading of that carbon dioxide. Why did that do that? So we will be experiencing loading down here and basically up top where the carbon dioxide is going to have a higher pressure within the arterial system, lower pressure within the alveolar space. We have the process of unloading taking place. And so you can see how the two of these guys work in tandem. And so just to stress the importance of this diagram, I leave this section with you. When we come back, which we will be doing very shortly, we will talk about specifically how exactly do we get the blood cell, or I should say the oxygen, how exactly do we get that oxygen from the lungs back down into the heart and back down into the much needed tissue space down below. And so that's the story of transporting oxygen. And that's what we'll look at coming up in the next session. As always, I encourage you to review, study. You can go back and listen to this as much as you want. Jot down some notes. Shoot me an email if you have any questions. I will do my best to further clarify if you are unsure of something. If you don't feel like emailing, jot it down and ask me during the next lecture session. But whatever it takes for you to succeed and be successful, that's what we want. This is Professor Young, wishing you luck and leaving you with this information until we meet again. Catch you later.